So we're going to learn about a way to actually improve some of these issues, and that is digital certificates. So the second approach, it's not going to fix all of them, but it's going to fix some of these properties, issues, and we'll see which ones. Okay? So basically, a digital certificate is just an association between a name and the public key by a CA. Okay, so it's basically an association between name and public key by a CA. What a CA is a certificate authority. Okay? And for example, I mentioned VeriSign is such a CA. Okay? So what can form a certificate? Well, it's a signature. Okay? So you have a signature using the secret key of the certificate authority, VeriSign in this case, saying Bob's, PK is, 0x54 blah, blah, and you also have an expiration date after which this certificate is no longer valid. Now you can assume that browsers have the public key of the CA. Browsers have the public key of the CA hard-coded. Okay. And then they can verify that, Bob's public key is indeed that. So some plus advantages of this is that anyone can serve Bob's public key now. You don't have to necessarily go to the trusted directory or to someone trusted to get Bob's public key. You can even ask an adversary, hey, what's Bob's public key? As long as the adversary is giving you this signature, then they cannot lie. Okay? So anyone can serve PK Bob. So we're going to call this the certificate for Bob. With a certificate for Bob, as long as the certificate is correct and it has not expired, then you can trust it, even if it's served by an attacker. Okay? And this, improves the issue of availability. Maybe if the trusted directory is not available for a moment, that's okay because you can get these public keys with certificates from different people. So it can fail, for half an hour or something and won't be too bad. But what issues would you say remain? So let's look back at the various issues. What issues would you say remain? Yes, it remains a central point of attack because that secret key of the CA is still used to sign every single certificate. Any other drawbacks? Yeah, exactly. You need to continuously update the key. Once the certificate expires, or you could set a big expiration date, but then that's a problem because what if, your key was compromised, then you're vulnerable for all that time until the expiry. So there's definitely a tension between how often you update the expiration date versus, how often you're vulnerable if your key was compromised. How long, yeah? Yeah, so it's in some ways similar, but you don't always go to the TD for every request. But you can ask, anyone around you. Maybe you can ask a local server that could have been compromised as opposed to going to the TD for the public key. Okay, so this is the main difference, is that anyone can serve the public key and the certificate for Bob. And then what Alice checks, she checks that, similarly, that cert of Bob, is, verifies with verifies with the public key of the CA. Public key of the CA is not expired. Okay, so this is a difference. We're not using nonces here, but expiration times. And also, it's for Bob, right? Namely, it says that it's Bob's public key. It says that it's Bob's public key. Okay, but the difference is that anyone can serve it. So you no longer need So Alice no longer needs to go to the TD, no longer contacts TD to fetch public key of Bob. You know, she can contact the local server or anyone. Okay, so there isn't so much of a point of failure, at least, I mean, of course, at some point it has to come back up, right, to update public keys, but if it failed for a moment or something, it's not such a big problem. Also, it helps with the burden on the certificate authority and this TD, because it doesn't have to be contacted for every request, okay? Yeah, so you can assume, but she can contact local servers, right? But she can contact local servers. For example, e.g., Bob's server, right? So she can go to what she thinks to be Bob's server. For example, if I want to talk to Bank of America, I go to what I think is Bank of America, and I say, can you please give me the public key for Bank of America? So I set up a secure connection. And, you know, even if it's not Bank of America, as long as I get the correct certificate, then I know that I can trust that public key for Bank of America. And if it's the correct Bank of America, then it's, you know, I won't have any issues. Yeah. Oh, that's such a great question. So the question is, how does a CA get authorized, and what stops an attacker from being a CA? There isn't a good answer to that. That's historically been a problem. So entities like VeriSign are trusted by reputation through time, but there've definitely been over time compromised CAs who some browsers recognized as CAs and trusted their certificates, and that's been a problem because then, you know, those CAs signed incorrect certificates. So that's been a huge problem, you know, for decades. And we'll see towards the end of the class in one of the miscellaneous lectures that there is a solution for that, again, thanks to blockchains and ledgers, the kind of new mindset, a decentralized mindset. But it's really based on reputation, and there are mistakes in that, you know, reputation system. There have been mistakes over time. In fact, there was a famous example where a CA gave incorrect certificate for Microsoft. I mean, even if they're well-intended, they can mistake. They can sign an incorrect certificate because, you know, they think, okay, this is Microsoft public key. Maybe they're talking to the wrong person. And that was a big problem because people had incorrect certificate for Microsoft, so the attacker could get them to install bad Microsoft software that had vulnerabilities. And that was a big problem because, you know, you could install a lot of software, and it was very difficult to revoke. We'll talk about revocation next time. But because Microsoft is Microsoft, they could actually blacklist that specific certificate since they were running on everybody's systems.